In this video, we'll continue a look at past paper questions on atomic physics, radioactivity, atomic physics, radioactivity, radioactive decay, right? Now, in this video, we'll look at a question from January 2015, paper 2, question 6, right? So, this question basically shows a uniform electric field, and of course, there's a radioactive source. So, part A of the question says, in order to separate the emissions from a radioactive source, they are subjected to a uniform electric field E perpendicular to their path as shown in figure 5. So we have the uniform electric field of strength E, and of course we have the radioactive source, which is going to be emitting three types of radiation: alpha particles, beta particles, and gamma rays. So part 1 of A goes on to tell us, describe the path of each of the three emissions, alpha, beta, and gamma, when subjected to a uniform electric field from left if the emissions are projected up towards the top of your page. So let's imagine that this, of course, is the top of our page. This, of course, is our electric field, and we have our radioactive source, right? Now, electric fields generally run from positive, or the more positive, to the more negative potential. In other words, then, electric fields will basically originate on the more positive potential and then terminate on the more negative potential. So what this basically means is that we can assign a positive charge or a more positive charge to this end and a more negative charge to this end. And this, of course, will affect the direction in which these particles will be deflected if they are deflected. Now, let's talk about alpha particles. What are alpha particles? Now, alpha particles are helium nuclei. What exactly does that mean? Being helium nuclei, alpha particles contain 2 protons and 2 neutrons within the nucleus. They have no electrons because they're not the helium atom, but just the helium nucleus. So, alpha particles, basically symbol alpha 42. So, they have 2 protons and 2 neutrons, and therefore they have an overall positive charge. So alpha particles are positively charged, right? Now, what about beta particles? Beta particles are fast moving electrons, and being fast moving electrons, it therefore means that beta particles will be of negative charge. So beta particles, beta minus 1, 0, they are of a negative charge, right? Now, what about gamma rays? Gamma rays are very short wavelength electromagnetic radiation and therefore do not carry any charge. So gamma rays, no charge. So what this means is that if this source is emitting alpha particles, gamma rays, and beta particles, then essentially the gamma rays will go straight through undeviated, right? So because gamma rays have no charge, they will not be affected by the electric field. Now, alpha particles are positively charged, and of course we know that like charges repel and unlike charges attract. So if this end is the more positive terminal or the more positive potential, and this end, of course, is the more negative potential, the alpha particles will be deflected towards the more negative potential, right? Alpha particles, however, are very heavy compared to electrons, and what this means is that the degree of deflection will not be as great as the electrons. So the path will not have a very it won't be a sharp curve. It will basically not have a small radius, a larger radius. So in the case of the alpha particle being deflected, we can say the path looks something like this. Slight deflection essentially, right? So a slight deflection towards the more negative end of the electric field, that is away from the positive end. So this would be the alpha particles, right? Now, electrons are negatively charged, and therefore they will deflect in the opposite direction. Now, because the electrons are much lighter than the alpha particles, the effect of the force of this electric field on them will be much greater excuse me, and therefore they will experience a much sharper deflection in the opposite direction. right? So we can see that the electrons or the beta particles will be experiencing a more sharper deflection, right? And essentially that is what is happening to those different forms of radiation which are emitted by the source. So once again, the gamma rays, which are short wavelength electromagnetic radiation, they have no charge and therefore are not affected by the electric field. Alpha particles are helium nuclei. They are positively charged and are therefore deflected in the direction that positive charge will be deflected, that is from the more positive end of the electric field or from the higher potential towards the lower potential. Beta particles are fast moving or high speed electrons. Of course, electrons are negatively charged and it therefore means that they will be deflected in the opposite direction to the alpha particles, but the amount of deflection will be greater due to the fact that beta particles or electrons are much lighter than alpha particles. Now, the second part of the question, that's part 2 of A, says if the electric field is replaced by a uniform magnetic field into the page, predict the path of the emission. So in the second part of the question, we're no longer concerned with the electric field, but with a magnetic field that is going into the page. Now let's represent our magnetic field going into the page. So just like we did when we used, when we're looking at a straight current carrying conductor, we use dots and crosses or dots and X's to represent the current going into the page, and coming out of the page. So in the case of the current, if the current is going into the page, you use X's. If the current is coming out of the page, you use dots. And it's a similar principle or concept when we're dealing with magnetic fields, right? So this basically shows a magnetic field going into the board, right? And once again, if we have our source, so if you have our source of radioactive material or source of or radioactive emissions, then essentially we will predict the direction of these the path of the emissions, right? So once again, gamma rays have no charge, and having no charge, it means that they will not be deflected by a magnetic field or an electric field. So once again, the gamma rays will go straight through undeviated. Right? So the gamma rays go straight through the magnetic field undeviated. Now, to predict the direction of the alpha particles and the beta particles, we must apply Fleming's left-hand rule, right? So Fleming's left-hand rule becomes important once again. Now, Fleming's left-hand rule, according to Fleming's left-hand rule, we place the first finger and the second finger of the left hand in the direction of the magnetic field and the direction of the conventional current respectively. And once we do that, the direction in which the thumb points gives us the direction of the thrust, the force, or in this case the motion of the charged particles, right? So we must bear in mind that the second finger must point in the direction that conventional current would flow. And when we speak about the direction in which conventional current would flow, we're talking about the direction of the movement of positive charge, right? So let's examine the case of the alpha particle first. Now once again, alpha particles are helium nuclei, and so therefore they're positively charged, and therefore whatever direction the alpha particles are moving in, then essentially that will basically be the direction of the conventional current. So this source is basically releasing emissions and they're basically moving into the magnetic field. So if the alpha particle is moving into the magnetic field, now the magnetic field is going into the board, right? So the magnetic field is going into the board and the alpha particles are moving upwards, and therefore because they're positively charged, the direction of this conventional current would be upwards. And so this leaves our thumb pointing to the left. Therefore, that means the alpha particles will be deflected towards the left. So let's do this again. Once again, the first finger must point in the direction of the magnetic field. The second finger must point in the direction of conventional current, and that is in the direction that positive charge would move. So in the case of the alpha particle, which is positively charged, the second finger will always point in the direction of motion of the alpha particles. So the magnetic field is going into the board. The alpha particle is moving up, and therefore the second finger must point up. And this leaves our thumb pointing to the left, which basically means that the alpha particles will be deflected towards the left. Now once again, because alpha particles are very large, especially when compared to electrons, their degree of deflection will not be as great. So they are basically slightly deflected in the direction that positive charge would be deflected. Right? So this would be the alpha particles. Good? Now, having done that, we will now do it for the electrons or the beta particles. So once again, beta particles are fast-moving electrons, right? And electrons, of course, are negatively charged. Now, the fact that electrons are negatively charged, when the electrons are moving, it means that the second finger will not point in the direction of motion of the electrons, because once again, the second finger must point in the direction of conventional current. Conventional current direction is a direction that positive charge would move, and therefore that is in the opposite direction to which electrons, which are negatively charged, would move. So if the electrons are basically moving upwards, it means that the second finger must be pointing downwards. And so we come like this. Our first finger pointing in the direction of the field, our second finger, which represents the direction of conventional current, must be pointing downwards because the electrons are moving up. So that is the direction of negatively charged. Negative charge is moving up, and therefore it means that positive charge and hence conventional current would actually flow in the opposite direction, and this means that electrons will be deflected to the right. Right? So we expect the electrons to be deflected to the opposite direction of the alpha particles. But once again, because these electrons are much lighter, or the beta particles, which are electrons, are much lighter than the alpha particles, they will experience a sharper curve. Right? So something to that effect, right? So basically, this sums up the directions in which the alpha particles and the beta particles will be deflected, and of course the gamma rays go straight through because they carry no charge and are therefore not affected by a magnetic field or an electric field. All right, so that was part 2 of A from this question, right? Now let's examine the next part of the question. The next part of the question, part B, says one isotope of lead, which is Pb21082, is not stable but can undergo exactly 3 distinct decays of an alpha or beta particle to become stable lead. With reference to the information in table 5, write a possible sequence of 3 nuclear equations that can result in Pb20682 stable lead from Pb21082, right? So let's create some space. All right, so this is information that we're given. We have this is essentially unstable lead. So Pb 21082, right? So that is unstable lead. Stable lead, of course, will have the same atomic number but a different mass number. So this is stable lead. Right? So of course they're isotopes of the same element, of course, so that they have the same number of protons but different number of electrons. Right? We're also given two elements and their atomic numbers. So let's just jot that down. So we have element, atomic number, so we have bismuth, Bi, with an atomic number of 83. And we have, what's that? Polonium. 2 L's or 1 L in polonium. Anyways, I'll spell it with 1 for now. We have oh, I didn't really need the word, to be honest, but anyways. So we have polonium, Po, and the atomic number is 84. Right? Now clearly, we're given these for a reason. And of course, we're expected to use them. Right? If we were not expected to use them, we would not have been given them. Right? So this is information that we have. We have unstable lead, proton number 82, mass number 210. Stable lead, proton number 82, mass number 206. And of course, we're told that unstable lead can undergo exactly 3 distinct decays of an alpha particle or beta particle to become stable lead. So eventually, unstable lead will undergo a few radioactive decay processes and eventually become stable lead. And we're given that clearly these elements, of course, will be involved in that transition process. And we're supposed to write a possible sequence of 3 nuclear equations that can result in stable lead from unstable lead. Now, before we go into that, let's briefly recap alpha particle emission and beta particle emission and look at the equations which govern both, right? So alpha particle emission. Right? Now once again, alpha particles are helium nuclei. So they have 2 protons and 2 neutrons and therefore have a mass number of 4. Whenever an unstable parent atom or parent nuclide undergoes emission of an alpha particle, the mass number reduces by 2 and the proton number decreases by 2. So if we let X represent the parent nuclide, X with a mass number A, proton number Z, it will emit an alpha particle, and emitting an alpha particle, it will form a new element, let's call that symbol Y, with a mass number of A minus 4 and a proton number of Z minus 2. And of course, we have our alpha particle, alpha 42, and of course, some energy is given off in the process as well. So therefore, what this means is that an unstable parent nuclide or parent atom will decay into a more stable daughter with a proton number 2 less, a mass number 4 less than the parent, and emit an alpha particle in the process. So during alpha particle emission, the mass number decreases by 4 and the proton number decreases by 2. Right? Now let's look at also beta particle emission, because this will be important as well. Right. Now once again, beta particles are high speed or fast moving electrons. And how exactly are beta particles produced? Beta particles are basically produced when the nucleus of the atom finds itself with too many neutrons to be stable. So essentially, a neutron is converted into a proton and an electron according to basically the reaction that looks something like this. So neutron, no charge, mass number 1 will basically be converted to, say, a proton, P, charge 1, mass number 1, plus an electron, no mass, charge -1, mass essentially 0, right? And this basically becomes this is our electron, which essentially becomes our beta particle, right? It is ejected from the nucleus and basically forms the beta particle, whereas the proton remains in the nucleus of the atom, right? So essentially, in the nucleus, a neutron splits into a proton and an electron. The proton remains within the nucleus, but the electron is ejected at relatively high speed and basically becomes the beta particle, right? Now, a neutron and a proton are virtually the same mass, and as a result of this, whenever a parent nuclide undergoes beta particle emission, the mass number does not change. So the general reaction for beta particle emission is this. We have the parent, X, with a mass number A, proton number Z, emitting a beta particle to form a daughter with a mass number A and a proton number Z plus 1 and a beta particle. Beta particle, charge -1, mass 0. And of course, we have energy being given off in the process as well, right? So basically, these two reactions are going to be very important in order to do what the question requires of us to do, right? So we looked at alpha particle emission, we looked at beta particle emission. Now let's go back directly to the question. So essentially, lead 21082 will undergo a few, what do they call that again? Transmutations, right? Undergo a few transmutations and eventually will produce stable lead, Pb 82206, right? Now, at some stage during the process, these elements, bismuth and polonium, will be formed. So we see that the atomic number of polonium is 83, whereas the atomic number of the atomic number of bismuth is 83, whereas the atomic number of polonium is 84. Now, if you look at unstable lead, how could unstable lead produce bismuth? The atomic number of unstable lead is 82 and the atomic number of bismuth is 83. So that's an increase of 1. So therefore, what this means is that in order to produce bismuth, unstable lead must emit a beta particle so that the proton number increases by 1 and the atomic number remains the mass number remains the same. So once again, in order to go from unstable lead with a proton number of 82 to bismuth with an atomic number or proton number of 83, unstable lead must emit a beta particle so that the proton number increases by 1 and the mass number remains the same. And the reaction is this. So this would be Pb 82210 to Bi 83, mass number the same thing, 210 plus beta particle, charge -1, mass 0, right? So that is one stage. Good. There's also polonium with a proton number of 84. So looking at this first example, we ask ourselves, how do we get to 84 polonium with an atomic number of 84 from this? Then what this basically means now is that bismuth is going to emit a beta particle to produce polonium. And the reaction is this. Bismuth 83, mass number 210, will form polonium with proton number 84, mass number 210, and emitting a beta particle. Right? Of course, energy is given off in the process as well. So this is the first, this is step 1, this is step 2, right? So the first two steps involve the emission of 2 beta particles, right? And now what do we see? Well, we've reached polonium with our atomic number of 84, but we need to get to stable lead with an atomic number of 82 and a mass number of 206. Now, how do we go from polonium with a proton number of 84 and a mass number of 210 to stable lead with a proton number of 82 and a mass number of 206. If we compare the numbers, we see that the proton number must decrease by 2 and the mass number must decrease by 4. And therefore what this means is that an alpha particle must be emitted by polonium in order to produce stable lead. Right? So I'll make some space for that. And so this reaction, this process looks like this. Polonium 210, 84 to lead 82, 206 plus an alpha particle, and of course energy being given off in the process, right? And this would be step 3 of 3, right? So essentially these are the 3 steps by which unstable lead can basically produce stable lead. So that was part B of the question, right? There is a part C of the question, and the part C says calculate the energy given off in a nuclear reaction, if the change in mass is 0.2014 atomic mass units. Why does this part of the question look very familiar? Anyways, calculate the energy given off in a nuclear reaction if the change in mass is 0.2014 atomic mass units. Right? Anyways, before we move on to that part, let's do a brief recap of what we have here. So essentially, part B of the question told us that one isotope of lead was unstable. It had a proton number of 82 and a mass number of 210. It basically decayed to produce stable lead by going through exactly 3 distinct decays to form stable lead, which is this. And we're also given this information, and we're basically asked to write the possible sequence of the 3 nuclear equations to result in stable lead from unstable lead. The fact that we're given these suggests that we had to use them, right? So therefore, to go from unstable lead to bismuth, unstable lead essentially had to emit a beta particle, right? By emitting a beta particle, the proton number increased by 1 and the mass number remained the same. Bismuth would then have to undergo beta particle emission to produce polonium with a proton number of 84 and a mass number of 210. That's the first 2 steps. And the third of 3 steps is that polonium will then need to undergo alpha particle emission to produce stable lead with a proton number of 82 and a mass number of 86. So moving on to part C of the question. Alright, so this part of the question says calculate the energy given off in a nuclear reaction if the change in mass is 0.2014 U. So part C, so the change in mass M equals 0.2014 atomic mass units. But you must recall, in order to calculate the energy given off, we must use the equation E equals mc squared, but in that equation M must be in kilograms, right? So U equals 1.66 times 10 to the minus 27 kilograms, and therefore M in kilograms is equal to 0.2014 times 1.66 times 10 to the minus 27, right? And this gives us a calculator. So 1.66 exponential negative 27 times 0.2014 equals 3.3432. Let's just call it 3.3432. Since we're in the middle of a calculation, we want to use as many decimal places as possible, right? So don't round off too quickly, right? In the intermediary steps. So 3.3432 times 10 to the minus 28 kilograms. And therefore the energy released E is equal to mc squared. So E is equal to 3.3432 times 10 to the minus 28 times the speed of light squared. So 3.0 times 10 to the 8 meters per second, and we square that. So this is times 3 exponential 8 times 3. And this gives us 3.009 times 10 to the minus 11 joules. Right? So that will be the energy released in this reaction. So this question was from, which was it? If I'm not mistaken, where is it? January, is it January? January 2015, right? So January 2015, paper 2, question 6.